Welcome. Today we'll talk about a few generative models. So this means we're going to use the data to estimate a density for each class, and we're going to use those density estimates to produce a prediction. So once we have an estimate for each class conditional density, which here is called Fi, so that's just going to be a probability density function or a probability mass function for each class I, and we also know the overall class proportions, then we're just going to use the largest Pi Fi value across the classes. So this is the Bayes classifier if the class conditional densities are equal to the underlying density of the data generating process. But if they're just estimates, then this will just be an estimate of the Bayes classifier. So this is not the only way to go about it. You can also try to produce a classification function that doesn't depend on any intermediate estimate of the density, but the models that we'll study today do. So the first one is called quadratic discriminant analysis. And the idea is that we just assume the densities for each class are multivariate Gaussians. So we just estimate the mean by averaging the observations that we get in each class, and we estimate the covariance matrix. The same idea. For each class, we form an empirical covariance matrix and use that to estimate the covariance matrix for the underlying distribution. And once we have that information, it's just a matter of working out what the class proportion times the class density is for each class at the observed feature vector, and then selecting the largest one. So we're going to use quadratic discriminant analysis on this famous data set called the iris data set. And the data we're going to look at look like this. So each flower has a sepal width and a petal width, which are recorded, each measured in centimeters. There are 50 flowers of each species, one shown in red, one shown in green, and one shown in blue. And we're going to see how the classifier works if we assume that each density is multivariate Gaussian with mean and covariance assumed from that particular class. So you can imagine here it's going to draw some line separating the red and the green, and then it's going to draw some line here that doesn't separate the blue from the green, but sort of does the best that it can. So we'll see how that works out. Okay, so there are various ways to go about this, but what we're going to do here is make mu, sigma, and n's dictionaries. So they're going to map the species names to the corresponding mean, covariance, and then also we're going to make a multivariate distribution object here. So for example, to estimate the mean for a particular species, we'll want to use the flowers object. So let's see what that looks like. It's a list of objects of type flower, and each one contains an X field which stores the feature vector, as well as a species field which stores a string representing the species of that particular flower. So what we can do is make an array comprehension over flowers in order to pull out these X vectors, because we're going to want to take the mean of the ones corresponding to a particular species. So if we do flowers, we get that. If we do f for f in flowers, if f dot species equals, let's say, this particular species, then we get just 50 flowers. They're just these ones. And we can also pull out the X vector so that we're not seeing the species there. So this is now a list of vectors, and we can take its mean. And that will be the centroid for those 50 points. So this is the value that we want. So let's put this here. And then we're going to do the same idea for sigma, except instead of the mean of the list of vectors, we're going to do the covariance matrix. And finally, once we have the mean and covariance, we can form a multivariate normal object, which represents that distribution. So to make a prediction function, let's take our class proportions and our normal distributions and then the feature vector at which to make a prediction. And we'll want to return the argmax, so the biggest value you get when we multiply each p by the corresponding density function evaluated at x. So we'll calculate the p-value for that species multiplied by the probability density function for that species evaluated at the observed feature vector. And then we'll loop over the keys of our species to color dictionary, which is storing the list of species for us. And we also need to calculate the proportions. And we can do this with something called proportion map. So if we look at the species, do f dot species for f in flowers, then we can count the proportions for the three species by just calling proportion map. And it tells us that each one is represented by 1/3 of the observations. So now we can make a heat map. And the function we want to heat map is the function that maps an x comma y pair to the prediction. And we have to supply this as a vector because the PDF function from the distributions package expects its input to be a vector if it's a multivariate distribution. And we'd like to see our points as well, although already we can tell this is doing something pretty similar to what we were hoping it would do. So let's package our scatter plot as a function so that we can call it again here. And what we can see is that this does a very nice job of separating green from blue from red. And that's reasonable because these data seem pretty plausibly to come from something like a multivariate normal distribution. So the assumption that each class conditional density is a multivariate normal is pretty reasonable, and so we're getting a lot of predictive value out of making that assumption and approximating these means and covariance matrices using the data that are available for each class. Okay, so linear discriminant analysis is closely related to quadratic discriminant analysis. The idea is that we're going to assume all the covariance matrices are the same for each class, but the means may be different. And the reason you might want to do something like that is if you don't have enough data to reasonably approximate the class conditional covariance matrices for each class. Usually you would in a low dimensional setting, but if you have a lot of features, in this case we're just looking at 2, but if you had many more, then you might have trouble estimating these covariance matrices, because a covariance matrix with p features has p squared total entries. Even if you account for redundancies with the symmetry of the matrix, there still are approximately p squared over 2 distinct entries to estimate. And if p is large, then that can be difficult, and so you might want to pool the data from all the classes to try to come up with an estimator. It turns out that the appropriate way to make an unbiased estimator in this context is to form the sum x minus mu transpose that you would normally compute to estimate a covariance matrix, and then divide by n minus c, where c is the number of classes. So this is a bit different from normal covariance estimation because you're using different mean values depending on the class. So typically when you estimate covariance matrices, you have a single mean, and the x minus mu vectors that go into the calculation are the ones from that mean to each observation. However, in linear discriminant analysis, we're using class-by-class means. So we're pooling all the red and blue vectors here into a single covariance calculation, but we're subtracting off different means based on the class. So since we're only going to get a single covariance matrix, we're going to start out by defining sigma to just be a matrix of zeros. So the mean for each species, just as before, is just the average of the feature vectors for that species. Then for sigma, what we'll do is add x minus mu times x minus mu transpose for each flower in that class. And we're adding this to sigma so that once we've looped over all the species, sigma will represent a sum of all of these x minus mu transpose values. Finally, we divide by 147, which is the number of observations, 150, minus the number of classes, which is 3. Now, once we know the correct covariance matrix for all 3 classes, we can define our multivariate normal distributions. So we want to reuse some of this code. Let's come back over here and package this heat map as a function. So the things we'll want to change are really just these p values and n values. So we'll make those the arguments of our function. And then we can reuse that here. And what we find is that we have linear boundaries separating the 2 classes. And this is a theorem. You can work it out to show that if you have 2 multivariate Gaussian distributions with the same covariance and you look for where they're equal, it's always going to be a line. So up here it can be a quadric surface, which in 2 dimensions is called a conic section. So just a solution of a quadratic equation here. The quadratic terms are going to cancel and you're going to end up with lines. So the linear and quadratic in the names are not assumptions built into the model, they're conclusions that you draw. And we see that on this data set they perform pretty similarly. Okay, so now let's talk about naive Bayes. Naive Bayes goes in a different direction with the assumptions that we're going to make. Rather than assuming that the features come from a Gaussian distribution, we're going to assume that they're independent. So this isn't incompatible. You could assume that they're Gaussian and that the features are independent. That amounts to assuming that the off-diagonal entries of the covariance matrix are 0. So you can think about mixing naive Bayes with quadratic or linear discriminant analysis. But because this is such a general idea, just features are independent, we can think about it in a discrete context as well. And in some ways that's easier to think about, and it's also more closely related to how naive Bayes is often used in the context of natural language processing. So here we have a set of data called X trained. So these are our features. And it looks like this. Our first feature is integer valued, and these are the observations that we get. Our second feature also integer valued, and the third feature is here. Now, I'll give you a second to pause if you like and see if you notice a relationship between the three columns. This third one is a sum of the first two. So the assumption in this case that the three features are independent is not valid. This third feature is always equal to the sum of the first two. So in random variable terms, you would say x3 is equal to x2 plus x1. Nevertheless, we can form an estimate of the underlying probability measure, which is based on an assumption of independence, and see what we get as a prediction function. We shouldn't be too surprised in this case if it ends up not working well because we made a faulty assumption. But in many real-world instances, the prediction function ends up being reasonably effective, even though it's based on an assumption about the features, which is ultimately not accurate. So these are our training observations. We have 80 of them, and they're arranged so that the first 40 are class 1 and the last 40 are class 2. What we want to do here, just to organize our code in a way that's compatible with scikit-learn, is define a new object called NB binary classifier, so naive Bayes binary classifier. And we need to declare it to be mutable because we're going to want to change some of these values during the training process. So the classes will be an iteratable object containing the different classes, in this case just a list or a range from 1 to 2. The class proportions will store the top level proportions. So in this case, it's going to be 50-50 for the two classes. And the conditional measures object will store the class conditional probability mass functions we get for the three features. So notice that we're going to do probability mass functions here rather than probability density functions because our random variables are integer valued. So it wouldn't make sense to talk about a probability density function since clearly the probability mass is concentrated at discrete specific values. And this makes our estimation life easier because if we want to say, what's the probability this first random variable is equal to, let's say, 5, well, we can just look at how many times 5 appears in this list and use that as an estimate. And similarly for the other ones. If we want to fit the binary classifier, which initially will be set in such a way that class proportions and conditional measures are bogus values, so this fit function is going to be populating those values, then what we need to do is first set the class proportions. So you access a field of a struct with this dot syntax. And the class proportions should just be the proportions of observations that we see. So if we do proportion map on ytrain, we see that class 1 is 50% represented, class 2 is 50% represented. So that's the right idea. Let's just call proportion map on ytrain. And the classes we'll assume have been set up correctly before we fit. So we just need to set the conditional measures now. And the idea is that we're going to need one conditional measure per class. So we'll make a dictionary just like this object is a dictionary which maps class indexes like 1 or 2 to their proportions. We'll set up a dictionary so it's going to map class J to, and then we'll have to come up with something here, but we'll fill out the back part of this comprehension for J in n.classes. So for each class, we're going to work out what's the collection of measures for each feature for that class. And the idea here is very similar as well. So we want to make a proportion map for each feature and for each class. So we'll index the training matrix and ask, where are the entries of this particular class? So first of all, we're going to select out only the training instances that correspond to the class we're looking at currently. And then we're going to look at the ith column. So I is indexing the feature and j is indexing the class. We have to look on a per feature, per class basis here. So we form that proportion map, and essentially that's the object we want. However, we have to keep up with this estimator for each feature. And the number of features is the number of columns, which is size of x comma 2. So we make I range over 1 to size of x comma 2. We'll have here now a list, in this case, of 3 proportion maps, each representing a probability measure. However, that's not good enough either because we might run into an issue. So let's see one of these proportion maps, see what we're talking about. So let's look at class 1 and feature 1. So this is the first column where we're looking only at the first 40 training examples. So 0 shows up 1/8 of the time, so that's the probability mass we're going to estimate at 0. 4 shows up 5% of the time, so that's the probability mass we'll estimate at 4, and so on. But notice here, we only see these values through 7, and an 8 could show up in a test example. Just because it didn't happen in the training set doesn't mean it can't happen. So if we give, so let's call this D or something, and if we ask what's D of 8, then we'll have a problem. So as long as we're between 1 and 7, it does the right thing, but we could easily run into an error here if we don't do something about this. So one kind of straightforward thing to do would be to just supply a bunch of extra keys so that we feel pretty safe that we're not going to get a number bigger than that. But there's a smoother way to do it, which is to define something called a default dict. So this is getting a little unwieldy, so we're going to pull this out. We're going to refactor here, and we're going to call this just probability dict for a particular class. So probability dict of j, that's going to be a function. So in this line, we're defining a new function that's local to this fit function that computes a probability dict for a given class j. And then we can call that function here, and now this line of code is much more comprehensible, and we just need to work on this line. So instead of just proportion map, what we want to do is create a default dict which returns 0 when the key doesn't match. So if you give it a key other than the ones that it has, it's just going to return 0. And we need to merge this default dict with no keys with this proportion map, which has some keys and values that we actually want to use. So in Python, the corresponding thing is the update method. It's first dictionary dot update second dictionary. In Julia, that operation is done with merge. Okay, and then this last line is going to return a value. It's going to return whatever this dictionary is. And it's sort of nicer when we call that function fit bang for it to not return anything. So we're just going to put nothing on the last line. That's a special object in Julia, and all it does is just not print anything if you run it in a cell. So it prints nothing, and it throws errors when you try to do stuff with it. So now we want to try to make a prediction based on these conditional measures. And here's where the naive Bayes assumption comes in. So we've estimated the marginal probability of each feature vector. In other words, we've estimated the probability mass function for its first component, for its second component, and its third component. And naive Bayes tells us we should just multiply those three values to get the probability for the triple. So again, in this case, it's not valid because of the way these data were generated, but we're going to pretend it is and see what happens. So we want to calculate the argmax of the likelihood. So let's make a function here too. Likelihood of j for j and n dot classes. So we loop over the classes. For each one, we compute this product of probability measures. So whatever value we see here, we're going to plug that into the estimator for the first component. Whatever value we see here, we plug that into the estimator for the second component. Same idea for the third one, then we multiply the 3. So that's what we're going to have to do here. So we compute a product across the 3 components. So here the length of x will be 3. And the value that we need to multiply is the conditional measure for the class of interest, which is j. So let's grab that. And then we need to look at the particular feature we're interested in here, which is going to be I. So now we'll be at a proportion map. So n.conditional measures is a dictionary whose keys are classes. So we've looked at the class we're interested in. Then we get a list, and the entries of the list correspond to features, so we've indexed that as well. So we're now focused on the particular class and feature we want to look at. Now we have a proportion map, which represents a probability measure, and we should look at the value that we actually get, which is going to be x bracket I. So this is the product of the measures. But then we also need to account for the class proportion. So this is just the f part. We don't have the p part, which we need to include as well. And then this is just a piece of convenience functionality. If we have a full test matrix that we want to evaluate the prediction function on each row for, then we just do that here by iterating over the rows of that matrix. So here's some test data that were generated from the same process as the original data. We need to define a binary classifier. So the classes are 1 and 2, and then we'll just put a placeholder in the second and third positions. And then we'll fit our model. So the model gets fit on this line, so that sets the class proportions and the conditional density estimates. And then we test it out on this new data, and we ask, okay, if we make a prediction for each of the rows in X test, and then compare them to each entry in Y test, how many are correct? It turns out to be 17 here out of 40. So that's really not good. And what you're seeing is that we're having a hard time estimating these probability measures accurately because we don't really have enough observations. And also the third feature here is not independent of the first two. So you can relax those two assumptions. You can define a function that generates a new training matrix for you, which gives you a lot more observations, and train on that data. And you'll see that the accuracy improves. And the other thing you can do is in the process of generating that training matrix, you can choose distributions for the different features, which are spread farther apart. So there's more differentiation, and the classifier will have an easier time telling the two classes apart. And you can also experiment with making the third column actually independent of the first two rather than being, in this case, just a sum of the first two. And that will also improve your accuracy because your naive Bayes estimation won't be based on a faulty assumption. However, you can get good results even with that broken assumption about independence if you have enough observations and if your distributions are pretty well separated. So finally, in problem 4, we'll talk about the game plan for building a naive Bayes classifier for identifying spam. And there's a homework problem where you'll carry this out. A body of an email is a string. It's not clear how to fit it into this framework where we have components and we're assuming they're independent. What are the components of a string? You could do it on a character by character level, but then you have the problem that the strings have different lengths, and it's also going to be very ineffective because it's a poor model of language to consider one letter at a time. One thing you can do that accounts for much more language structure, but is still very simple, is to identify a vocabulary of common words. Let's call it W. This might be the 2,000 most common words, let's say. And then you associate each email message with a vector X, which has length 2,000, if 2,000 is the vocabulary size, and consists of zeros and ones. So an entry of 0 indicates for that particular message that the corresponding word is not there in the email, and an entry of 1 represents that the word is there. So this is a very simple model, but it turns out to do a reasonable job when it comes to email classification. So for example, let's suppose we just have this very short vocabulary, the, are, gift, click, money, baseball. We want to vectorize each of the following sentences according to this scheme. So are you going to the baseball game? So we'll just go through the words one by one and see if they're there. So the word the is in this message, so that's a 1. The word are is in the message, that's a 1. Gift is not there. Click is not there. Money is not there. And baseball is there. So this email corresponds to the vector 1, 1, 0, 0, 0, 1. So in this case, the is there, so that's a 1. Are is not there. Gift is there. Click is there. Money is not there. And baseball is not there. So hopefully with these examples, you can start to see how spam and non-spam messages are distinguished from one another. It's just by the vocabulary that they use. So if there are words that tend to appear more often in spam messages, you'll get ones in those positions more, and you'll get separation along that axis. And you have a lot of axes to consider here. So in aggregate, you might end up with a substantial amount of predictive ability, even with this very crude model. So question B asks us, how should we estimate the probability that x1 is equal to 1? Well, that's just the event that the first word in our vocabulary appears in a given message. So we can just consider all the legitimate messages in our corpus and ask whether that word appears. And then same idea for the spam messages. So just to put a point on how contrived this model is, this question asks us to think about how we would generate an email which really does conform to the probability measure we're assuming on this vector of ones and zeros. This is a product measure. We're assuming independence between the features, that is to say independence between the different words. So the process being assumed here implicitly is that we loop through our vocabulary, and for each word, independently of all the others, we just decide with some small probability to incorporate it into our message or omit it. And that probability just depends on how frequently that word appears in the type of message we're writing. So in summary, generative models are models that are based on an estimate of the underlying density or mass function. Quadratic discriminant analysis is an example of a generative model, and it just assumes that the class conditional densities are multivariate Gaussian. Linear discriminant analysis is the same idea, except that we assume that the classes have a common covariance matrix, and we pool data from all the classes to estimate that common covariance matrix. In the end, it turns out that for quadratic discriminant analysis, the decision boundaries are quadratic surfaces, and for linear discriminant analysis, the decision boundaries are planes. Finally, naive Bayes assumes that the features are independent, so that's got to be coupled with another method of estimating densities for each feature individually. For example, you could use kernel density estimation, you could use a Gaussian assumption, or if it's a discrete measure, you can just estimate the probability mass at each value based on the proportion of training observations you see at those values.